This is Physics, Lab 2, Experimental and Predicted Data Comparison for an object dropped from rest experiencing drag forces using Python and Tracker. As seen in the next video, a small paper crumpled into a ball dropped from 2.5 meters. Okay, this is a screenshot of the Tracker program. This shows the experimental setup. We were dropping a crumpled piece of paper. We have 2 meter sticks attached to this wall, and we put some red tape at the beginning and the ends of the meter stick for a calibration system. This is just a short clip to show the Python module running with the drag coefficient times the velocity squared. I'll show the initial conditions and calculation loops just after this. There we go. Now hopefully you can read this. These are the initial conditions. We had a crumpled piece of paper with weighing a few grams. The ball position had been set to 0 and the initial velocity was also set to 0. We used a time step of 0.033 to match the iPhone we were working with. This is the magnitude of G near the Earth's surface. J hat pointing in the downward direction, and this is the final proportionality constant for B for the drag force that we arrived at to match our experimental data. This is the calculation loop I used for the crumpled paper ball. We dropped the paper 2.5 meters, so less than a second. Our 0.7 seconds was fine here. This is the weight of the system. This is just the mass of the ball times G, 9.8 times J hat in the downward direction. This is the drag force calculation. This is the drag coefficient times the velocity squared. A little tricky. I had to look up the magnitude of the ball velocity, how to do that in Python. So we have the drag coefficient times the magnitude of the ball velocity times the magnitude of the ball velocity, which gives you the velocity squared, times a vector pointing downward in the y direction. This is the net force, the weight, plus Newton's second force. This is the recalculation for the new velocity, and this should look familiar. This is just a new prediction on the ball position, and we advanced the clock delta t. We recorded the data with Tracker, and we've got a graph output here. A small amount of data outputted to the Excel file for no drag, drag proportional to BV, the assignment drag proportional to B times the velocity squared, the experimental results in our adjusted value, which turned out to be, after a few iterations, 1/2 the value that we used in class, so 0.0008. All right, here's the results we received, graphed out for the crumpled paper ball drop, the experimental versus the predicted. We have 0 drag in blue here. The red is with a drag coefficient B times the velocity. The experimental is purple. That actually ends right here, but it's a fairly good fit with just B times V. And we have the initial drag force times the velocity squared was out here. We did some adjustments. We cut the value down in half by trial and error, and we arrived at a fairly close fit on the curve. So both the B times the velocity and the B times velocity squared was a good fit on this graph. What does it mean? Which models predict terminal velocity? Well, in actual fact, both cases predict a terminal velocity, but with 2 different terminal velocities. In the first case, we modeled the drag coefficient times the velocity squared in Python. We extracted the data, came up with this graph, and determined the terminal velocity was just about negative 7.4 meters per second. In the second, where we had the drag coefficient just times the velocity, we arrived at a terminal velocity of negative 25.9 meters per second. It just means here that the drag coefficient times the velocity squared would dominate, and we'd reach terminal velocity a little bit faster than in the second case. The object was initially thrown downward. Would the terminal velocity be the same or different from the case where it was initially dropped from rest? In this, I used our Python model where we had the drag coefficient B times the velocity squared. We set the initial velocity vector to 8 meters per second downward, and we ended up recording the same terminal velocity, 7.424 meters per second, as we did when it was dropped from rest. So we had some good agreement.